Real numbers. Before starting with our actual topic, let us understand with the basic first. First, natural number denoted by n. Here, n is equal to 1, 2, 3, 4 and so on. Second, whole number which is denoted by w. Here, w is equal to 0, 1, 2, 3 and so on. Third, integer which is denoted by I. Here I is equal to -3, -2, -1, 0, 1, 2, 3 and so on. Diagram of classification. Real number which is denoted by R is classified into two types of numbers. Rational number which is denoted by Q and irrational numbers which is denoted by Q dash. Rational number is classified into two: integers which is denoted by I and fractions, and irrational number is classified into two: positive and negative. And further, integers are classified into three types: positive integers or natural numbers which is denoted by n, 0 and negative integers. Rational numbers. The set of fraction is called a rational number. Here, q is equal to p by q, where p and q belongs to integer and q is not equal to 0. Equality relation on q. If PS is equal to QR, then P by Q is equal to R by S. Order relation on Q. If PS is greater than QR, then P by Q is greater than R by S. Properties of rational numbers. A. Properties of addition of rational numbers. If A, B and C are any rational numbers, then let us assume that A is equal to 3, B is equal to 4 and C is equal to 5. First, commutative property, which is A plus B is equal to B plus A. Therefore, 3 plus 4 is equal to 4 plus 3 and hence 7 is equal to 7. Second, associative property. A plus B plus C is equal to A plus B plus C. Therefore, 3 plus 4 plus 5 is equal to 3 plus 4 plus 5, which is 7 plus 5 is equal to 3 plus 9, which comes to 12 is equal to 12. Third, additive identity. A plus 0 is equal to 0 plus A, which is equal to A. Fourth, additive inverse. A plus minus A is equal to 0. For example, 3 plus minus 3 is equal to 0. B. Properties of multiplication of rational numbers. Here, let us assume A is equal to 3, B is equal to 4 and C is equal to 5. First, commutative property. A into B is equal to B into A. Therefore, 3 into 4 is equal to 4 into 3, which is 12 is equal to 12. Second, associative property. A into B into C is equal to A into B into C. So, 3 into 4 into 5 is equal to 3 into 4 into 5, which is 12 into 5 is equal to 3 into 20. Therefore, 60 is equal to 60. Third, multiplicative identity. A into 1 is equal to 1 into A, which is equal to A. Fourth, multiplicative inverse. A into 1 by A is equal to 1 by A into A, which is equal to 1. Fifth, distributive property. A into B plus C is equal to A into B plus A into C. For example, 3 into 4 plus 5 is equal to 3 into 4 plus 3 into 5. Therefore, 3 into 9 is equal to 12 plus 15, which is 27 is equal to 27. Sixth, if A into B is equal to 0, then either A is equal to 0 or B is equal to 0, as the multiplication with 0 will give the answer 0. Irrational numbers. Numbers which are not rational numbers are called irrational numbers. For example, square root of 2, square root of 3 and square root of 5. Note: decimal fractions with non-terminating and non-recurring, that is 0.011011100 and so on. Now we will start with our actual topic, real numbers. Rational numbers and irrational numbers. Properties of order relation on real numbers. First, A is equal to B, or A is greater than B, or A is less than B. Second, suppose A is equal to 3, B is equal to 4, C is equal to 5. Therefore, if A is less than B and B is less than C, then A is less than C. For example, 3 is less than 4, 4 is less than 5. Therefore, 3 is less than 5. Third, if A is less than B, then A plus C is less than B plus C. For example, 3 is less than 4. Then 3 plus 5 is less than 4 plus 5. Fourth, let A be less than B. First, if C is greater than 0, then AC is less than BC. For example, 3 by 5 is less than 4 by 5. And second, if C is less than 0, then AC is greater than BC. If C is equal to minus 2, then 3 into minus 2 is greater than 4 into minus 2. Absolute value. First, modulus of x is equal to x for x is greater than 0. For example, if x is equal to 5 greater than 0, therefore modulus of 5 is equal to 5. Second, modulus of x is equal to minus x for x is less than 0. Third, modulus of x is 0 for x is equal to 0. Euclid's division lemma. Theorem: given any positive integers a and b, there exists unique integers q and r satisfying a is equal to bq plus r, where 0 is less than equal to r and r is less than b. Here a is the dividend and b is the divisor, q is the quotient and r is the remainder. Euclid's division algorithm is a technique to compute the highest common factor HCF of two given positive integers. For example, let a be 25 and b be 5. According to Euclid's division lemma, here a is equal to bq plus r, which comes to 25 is equal to 5q plus r. So, 5 divided by 25. Here we get 5 as the quotient and 0 as the remainder. So, b is equal to 5 is the HCF. Method to find HCF of two positive integers. Step 1. By using Euclid's algorithm, find q and r such that a is equal to bq plus r, where 0 is less than r and r is less than b, Step 2. If r is equal to 0, then HCF is b. If r is not equal to 0, apply the algorithm to b and r. Step 3. Continue the process till the remainder is 0. For example, let a be 20 and b be 10. A is equal to bq plus r. So, 20 is equal to 10 by 2 plus 0. And hence, 10 is the HCF. Let's take another example. Let a be 35 and b be 14. A is equal to bq plus r. So, 35 is equal to 14 by 2 plus 7. A is equal to bq plus r. So, 7 into 2 plus 0. Here, 7 is the HCF. The fundamental theorem of arithmetic. Theorem: every composite number can be expressed or factorized as a product of prime factors, and its factorization is unique, apart from the order in which the prime factors occur. This fundamental theorem helps us to find HCF and LCM of the numbers. For example, 9 and 12. 9 is equal to 3 into 3, which is 3 square, and 12 is equal to 3 into 4, which is 3 into 2 square. Here, the HCF is 3 and the LCM is 3 square into 2 square, which is 9 into 4, which comes to 36. Surds. Irrational root of a positive rational number is a surd. Nth root of a, or a raised to 1 by n, if n belongs to n where n is not equal to 1. Note, n is the order of surd, a is the radicand, and square root is the radical sign. If n is equal to 2, then it is a quadratic surd. Forms of surds. First, mixed surds. K nth root of a. When k belongs to q, k is not equal to 0 and k is not equal to plus or minus 1. For example, 2 fourth root of 7. Second, pure surd. K nth root of a, where k belongs to q and k is equal to plus or minus 1. For example, fifth root of 9. Similar surds or like surds. P nth root of a and q nth root of a, where p and q belong to q. For example, 3 by 7 root 2 minus 12 root 2 are similar surds. Simplest form of a surd. Comparison of surds. Surds of same order can be compared. First, nth root of a is equal to nth root of b, if a is equal to b. Second, nth root of a is greater than nth root of b, if a is greater than b, and nth root of a is less than nth root of b, if a is less than b. Operation on surds. First, addition and subtraction only on like surds. For example, 3 root 3 plus 10 root 3 is equal to 3 plus 10 root 3 is equal to 13 root 3. Second, multiplication and division can be done using law of surds. For example, 3 root 2 into 4 root 3. The order of the surds is 3 and 4. Therefore, LCM of the order is 3 into 4, that is 12. For example, 3 root 2 into 4 root 3 is equal to 3 by 4 root 2 raised to 4 into 4 by 3 root 3 raised to 3, equal to 12 root 16 into 12 root 27, which is equal to 12 root 432. Rationalization of surds. If the product of two surds is a rational number, then each surd is called a rationalizing factor of the other surd. For example, 2 root 2 into root 2 is equal to 2 into 2, which is equal to 4, which is a rational number, and hence 4 belongs to Q. Binomial expression of quadratic surds. General expression is a plus y root of b, where a belongs to Q, a is not equal to 0, or a is a quadratic surd. Y belongs to Q and y is not equal to 0, and hence root b is a quadratic surd. Conjugate pair of surds. The binomial expression of quadratic surds a plus y root of b and a minus y root of b is said to be the conjugate of each other.